Hello, welcome to Munro Live podcast. Yes, we have a very interesting guest here today, Dr. Vincent Pluvinage. He is a serial entrepreneur, I would say. He started his career at AT&T Bell Labs, and shortly thereafter ended up spinning out a corporation that was related to hearing technology, and then ultimately some intellectual property management entities, and then ultimately found his way to OneD. OneD Science company. It's a battery sciences company. They are famous for a product line called Sananode. Now, am I pronouncing that correctly, Sananode?
Perfect. Thank you.
Oh, perfect. So Vincent is here to tell us about his company and a little bit about his past. And with that, I start my own research and looking at part of his past, very interesting past. I could talk the whole day about his past, but we're going to try to focus on the present and the future. But in his past, he's got a vast patent portfolio, over 100 patents with his name on it, which is pretty honorable. Congratulations on that. Some of those are, of course, focused on OneD, his current company. So we'll talk a lot about that here. But, in what ways did this vast background of yours pave the way or prepare you for what is now your role here at OneD?
Well, first, thank you for having me. I'm an avid watcher of the videos from Munro because I love the teardowns and I've watched hours and hours. Yeah, so I have a background in physics, basically, but I also studied medicine and did some bioengineering. That's my PhD. And then I created this first company out of Bell Labs, which is called Resound, where I tackle the miniaturization of the technology into a silicon chip that was very powerful, but needed to be very small to fit into the ear canal of people, and also needed to work on a tiny little battery, which was very, very difficult. And I know it was difficult from the start because my first two investors were Andy Grove and David Packard. And they told me that making the kind of processing of the sound in that size chip with that kind of battery was not going to be easy. And they knew more than I did, of course, after about semiconductors. So I think that my background has helped me as far as the last 10 years in the battery industry in three ways. One way is that I've been an avid reader of the technology progress of silicon, whether it's silicon for chips, silicon for solar cells, or silicon for optic fibers. And silicon is now getting in the hot seat for batteries. And there is a lot of things about this element of the periodic table, both from a technical and scientific point of view and from an economic point of view, that is fascinating. So that's one area. I think the second area, which I learned over the years, is that batteries are actually very complicated from a scientific point of view, much more complicated, for example, than semiconductor technology, because electrochemistry modeling of lithium-ion batteries is more of an art than a science, in the sense that there is many, many different scales of models, but you cannot do the same kind of simulation you would do on a semiconductor chip. And that has led the industry to progress with a fair amount of trade secret, especially in large-scale manufacturing. And that's quite different from other fields that I know. And in biology, there is also the same kind of problem. So if you study hearing, there is really two sides to it. The treatment of the sound, which is, of course, electronics and physics, and then the way we perceive the sound, which is, of course, the biology of the human ear and the human brain. And I would say that respect for what we don't know when you try to understand batteries is a great way to approach the problem. There is a lot of things about how a lithium-ion battery works, which you learn in a lab, and it's not fully understood at the scientific modeling level. And I think the third aspect of my background is that I understood early on, after I met early in my career, Ray Dolby, the role of intellectual property in basically innovations and how one could build a business model which would be less capital intensive and really promote innovation, but also promote adoption. And so when I approached our CTO, Yimin Ju, who is an inventor on almost all of our patents at OneD, he showed me the first year I met him in 2012, all the patent applications that he had filed at the time. He started working on this technology called Synanode in 2007. And I spent a year reading those patents and talking to him and getting educated. And I understood at that point that this is going to be a long road to scale up and in performance, in volume, and decrease the cost. But because of the IP, it was worth my time and the investment of a group of investors I put together. So in a nutshell, those are the three elements of my background that have played a role in this adventure. Silicon, biology, and patents.
All right, very nice. If you look at your background, it kind of looks like you almost reinvented yourself, but with that explanation, no, it's a very clear segue where you're leveraging your past to the future. So I certainly appreciate that detailed explanation. So I have another question. 100 patents with your name on it. Fascinating. Are there any that stand out as critical or maybe your best achievements or accomplishments that you can briefly describe?
Well, there is a couple that I think are kind of interesting. The first one had to do with understanding how the product we had designed, i.e. this very sophisticated programmable hearing aid, was going to be distributed by the distribution channels. And, one of the problem about creating a very sophisticated chip that can be adapted to the hearing of each individual is that you need to be able to program it with the parameters that are needed for that person. And that's going to be different than from another person. And then you're dealing with the only thing that matters is the perception of the end users. You cannot get into their brain. So it's more about the perception of the sound than it is about the physics of the sound. And so we were confronted with the problem that when a hearing aid has only 3 little screws that you can adjust with a screwdriver, then the audiologist can basically find a way to adjust these little screws based on some testing and conversation with the patient. But when you have more degrees of freedom, also comes a bigger problem is how do you manage the degrees of freedom to deliver the benefit? And so I came up with an invention way early in my career, which was to design a small computer that provided a series of various different types of sound in terms of frequency and loudness to the patient and automatically records the answers. And then out of that essentially feedback loop, create the parameters that can be programmed into the device and then adjusted by the audiologist. And what that gives me an appreciation for as an invention is how important the feedback loop is from the customer back into the technology. That it's not right to think that you can design a technology and then say, this is the greatest thing since sliced bread. It's a silver bullet. It solves all the problem. World doesn't work that way. Almost any technology, actually any technology that I know, requires customer feedback loop and optimization. So that's an invention that I carried in my head because it made the distribution of the product much more effective, but it also made me understand how this feedback loop from the customer into the technology works. And then another completely different technology, I invented a way to produce the perception of sound using light. And that basically was a way to have a little optic fiber in the ear canal, which has a laser beam that goes into a contact lens on the eardrum, and then through a mechanism vibrates the contact lens, which gives the perception of sound. And creating a way to use different kind of technologies in a unique way is something that got me fascinated when I learned about the invention from our CTO, Yimin Ju, because essentially his approach to the problem of how to develop a better technology for lithium-ion battery had twofold. One was a scientific approach about how could silicon work, and the other one was a pragmatic approach, is what can I use that already exists to make it a lot easier to scale in manufacturing, a lot less expensive in manufacturing. And I've rarely seen people able to do both. And I think that my inventions in hearing allowed me to better understand the value of his invention in batteries.
Very nice. So, yeah, the mixed medium of light and sound, that's fascinating. So, again, I hate to linger on the subject, but 100 patents. How do you manage such a vast intellectual property portfolio? That would be a full-time job for most people, I think. So you must have some tricks.
Most of my patents predate OneD, and so they are managed by the companies that acquire my previous companies. I think most of the patents at OneD, Yimin Ju, our CTO, I'm a co-inventor with him, and I think only on one or two patents. And I think that you're quite right. From the day we started on January 1st, 2014, after we acquired the technology, the IP, the team, the equipment from the predecessor company called Nanowires, we realized that this was essentially a diamond in the rough, and that it would take years to go from what is patent applications to a portfolio that is granted in many different countries, whether it's Korea, Japan, China, United States, Canada, Europe, and so on, with broad claims that can defend the materials, the manufacturing process, and the equipment. And so I ended up recruiting a person that I'd worked before, Carlos Gantini, and he worked with me in two previous companies, and he learned how to manage essentially IP portfolio. And so he has a dual role at OneD, which is on the one hand, he's the CFO, on the other hand, he's the head of IP. And another example is I have a friend that I met 20 years ago, a fantastic patent attorney, and he worked for a big law firm and as a partner. And so for the first 10 years of the company, we used that law firm because I always thought that he understood both patents from a legal point of view, but also the practical side, which is the business aspect. And then early this year, he actually came to me and he said, I want to resign from the partnership of this big worldwide law firm and come full time. And he's now, Ron Lopez is our chief licensing officer and general counsel at the same time. So we have spent in the last 10 years between $500,000 and $1 million a year, basically on the patent portfolio. So this takes a lot of time. And I would say it takes a lot of expertise, a lot of money, but also a lot of reading. And so as an example, I probably personally read over 2,000 patents on silicon anode materials and probably about 2,000 or 3,000 scientific articles. We actually have a tool that runs every Sunday that uses very sophisticated search in all the patent office around the world to extract whatever new patent application is getting published during the previous 7 days that relates to our business. And then I get an automatic email and I spend, the Sunday evening going through the spreadsheet and seeing what are those essentially footsteps in the snow indicating about the trend of the industry. And it's interesting because people invest in R&D, they file inventions on whatever they think is valuable. 18 months later, that gets published well before there is a product announced. And if you look at the name of the people, where they work, and what they are putting in those patent applications, you essentially have a unique channel to understand what is the R&D investment of the world in my domain looks like. And that's fascinating because it's a little bit of view in the future, if you wish.
Oh, yeah, very nice. I'm sure it also affords your opportunity to make sure that any new, application claims aren't prior art of your own, such that you might need to contest such a patent application. But let's save that for another discussion. let's talk about OneD and all the very many interesting aspects of the company you work with now. So I'll start with kind of a more generic question that talks about our anode supply chain here in the United States and North America in its entirety. It's pretty weak, and it's a bit of a panic when you look at the trajectory of the electrification business here. It's on a slope that's going to be really hard to maintain, especially as we continue to try to leverage foreign resources to achieve that slope, if you will. So, you've got some thoughts on how that might get fixed, if you will. How can we fix our North American supply chain as it relates to anodes for lithium-ion batteries?
Actually, it's an excellent question. And let me first with deepening the problem and then maybe indicating some solution. So if you look at the anode is essentially for lithium-ion batteries used in EV almost exclusively graphite today. There's a little bit of other things like silicon powder, silicon oxide, but the vast majority of the weight of all of the EV cell batteries on the anode side is graphite. Maybe, 60, 70 kilograms of graphite per EV battery. It's the number one weight in an EV battery.
It's like 25-30%, I think, right?
Yeah, so it's a big chunk. And one thing that is difficult for people to grasp is that the raw materials of graphite comes either from petroleum coke or from mined graphite. But that's not suitable for use in batteries. What is suitable is something that has been processed. And the processing is not easy. You have to remove impurities, you have to shape the particles so that they have a certain dimensions, and you have to do certain coating to establish the fact that they should be stable in the battery over 1,000, 2,000, 3,000 cycles. And all of that processing requires large investment and a lot of energy. And if you roll back the tape, maybe a decade ago, the leaders in that field were initially Japanese companies like Hitachi Chemical and Mitsubishi Chemical, and also some Korean companies like POSCO. And then when about 5 years ago, the sales of EVs started growing, with Tesla asking their suppliers to invest in larger capacity and reduce price. Essentially, the Chinese suppliers agreed to make enormous amount of investments, hundreds and hundreds of millions of dollars, into increasing the supply of synthetic and natural graphite, while at the same time reducing cost, i.e. reducing the price at which they were selling the graphite to the EV cell makers. And that's a strategy that had worked in solar cells, because solar cells were invented in the United States and in Europe. But if you look today, 93% of all the solar cells are made in China. And the same trajectory went for a lot of materials in the battery space, where the processing of those materials was made in China for essentially three reasons: availability of very inexpensive capital, speed at which you could permit the factories, and then the availability of a lot of energy, especially coal plant energy in Mongolia that could supply, without regards for carbon footprint, very cheap energy in very large quantities. And as a result of that, today, virtually 100% of the graphite used in the EV cell factories in the United States and in Europe is imported from China. And as you know, as of yesterday, there is basically new regulation in China that is going to restrict some of the export of those things. And the question is, how do you get supply chains in America or in Europe? And so there is large amount of reserves of natural graphite. There is plenty of petroleum coke. And there are some companies that are already been investing for a decade. A couple of examples, one in Louisiana called Sierra Resources, publicly traded, with a mine in Mozambique. They have an offtake agreement with LG and with Tesla. And another one in Canada called Nouveau Monde Graphite in Quebec, who has been, a fantastic mine of 350,000 tons underground reserves, but small manufacturing operation today and an offtake agreement being negotiated with Panasonic. And so you would say, well, that's pretty simple. That's two examples amongst others. There are also companies in the synthetic graphite like Novonix and Avignon and so on. So they should have no problem scaling up and offer an alternative to the OEMs and EV cell makers. And the same thing is true for POSCO, a Korean company. The problem actually is an economic problem, is that if you're trying to do project financing and you say to the customers and the bankers, in order to go from, let's say, 5,000 tons of processing, which is a demonstration level processing, to, let's say, 40,000 tons manufacturing capacity of EV grade graphite, I'm going to need $800 million. And it's going to be 600 million in debt and 200 million in equity, for example. And you try to raise that money to scale up. You need a business plan. And that business plan has a bunch of numbers where the fundamental assumption is the price at which you can sell the graphite to the OEMs. And of course, the advantage is that graphite coming from North America is better from the point of view that the US government is offering a rebate of $7,500 per car if you source enough of the material in North America. So you put those things together, it should be a no-brainer. That's not the case. It's very difficult for a couple of reasons. One is that the incentives will disappear at some point in the future, because as we have more and more EVs being sold, the government cannot afford to pay $7,500 per EVs. So any of the OEMs that is planning for their production has to take into account what is the right cost for the material I'm buying to put in the EV cell that goes into the battery pack that goes into my EVs, so that I can reduce the cost of the battery packs and make affordable EVs, which is the majority of the market. And therefore, they have to assume what is the price without the benefit of the incentive. And the second piece is the bankers that are trying to raise the debt say, well, what happens if the OEMs choose to buy, natural or synthetic graphite that are imported from China, which even after tariffs can be purchased for $5-6 per kilogram instead of the $8 or $9 per kilogram in the business case of the North American supplier. And now if you try to decrease the $8 or $9 per kilogram to 5 or 6, suddenly there is not enough profit margins to pay off the debt, and the project financing is very, very hard. And so the problem for North American supply chain is not just an issue of resources or talent or expertise or permitting, all of which, of course, exist, but it can be solved. It's fundamentally, how do you compete against a country that can export vast quantities and that they've spent the last 5 to 10 years developing the production capacity to the level where the economy of scale allows them to sell with no profit or very slim profit at a price that nobody else can compete with. That is the problem.
Now, didn't we just help the problem, though, with China and their new restrictions? It should limit the supply at that low price and maybe cause the price to go up and help everyone's business case to do the investment. I'm knocking wood, hoping that's true.
Yeah, that was the hope when United States imposed tariffs on solar cells, and China responded with tariffs on polysilicon. And at the end of the day, those tariffs work exactly in the opposite direction in the long term. So I don't think that's the solution. It may help in the near term. It will not help in the long term. So I've been thinking about this exact problem for more than a decade. And I'll share my very simple view about this. There is only one way to compete, and that's innovation. And let me explain what that means by innovation. Innovation is process innovation in which the West, whether it's United States or Europe, can come up with things that are new and patented, which increase the value and decrease the cost, so that you can react to the customer needs to have lower cost batteries on the one hand, which is a must. And at the same time, if something that is protectable because of the patent law, so that it cannot simply be copied in China or in Brazil or in Malaysia and exported to the United States. And this has worked well in other industries. If you take semiconductor, okay, in semiconductor, there is a bunch of rules that have acted to support what we call Moore's law. So those rules are essentially two types of rules. One is the specialization of various companies in the supply chain for semiconductor. And the other one is the IP strategy of the industry. So if you look at semiconductor chips today, the West has still a 10-year advantage over China. So you have TSMC in Taiwan that can buy very, very sophisticated extreme UV lithography from a Dutch company in Holland called ASML. And that's well in advance of any machine that exists in China. It's protected by IP. And the IP from the chip design point of view, you can get it from ARM, which is a UK company that recently went public. And then companies like Apple can actually take the ARM semiconductor IP to design the Apple silicon. And then that Apple silicon chip design can be shipped to TSMC in Taiwan that use the ASML factory equipment to produce the world's most sophisticated wafers with the most incredible chips that you find in your MacBook Pro and MacBook Air and AirPods and iPhone. And that has worked. And that has worked because the industry organized itself in a way that the supply chain leverages innovation in a very cogent business model. And I think that what needs to happen in the battery industry is something similar to that.
I see. Okay, well, and innovation is ongoing. We'll talk a little bit more about that later here. But, you know, I have some fundamental ponderings, if you will, related to your nanowire technology. You know, first, why nanowires? Why not some other form, right? Silicon has a lot of different ways it could be implemented in an anode, but you chose the nanowire. Well, why is that best?
Yeah. You know, that's also something I asked myself 10 years ago before deciding to invest. And so let's first start with what has been known for about 20 years about silicon and lithium-ion batteries. The first thing is that everybody knows for 20 years that you can store more lithium in silicon per gram of silicon than you can do in graphite, about 9 or 10 times more. But everybody has known for a very long time that when you alloy lithium and silicon, the silicon blows up, the volume expands.
Yes.
And then when you release the lithium, it contracts. And those variations in volume are much greater, maybe 300% variations between uncharged and charged or alloyed silicon than it is for graphite. And so that has been a big problem that everybody has known. And what was discovered is that when you blow up the silicon by essentially injecting lithium and electron, if the particle is too large, it will break.
I see.
But if the particle is below 100 nanometers, which is very, very small, a nanometer is 10 to the minus 9 meter. So it's about, it's about 20 thousandths of the diameter of a eyelash. If you do the powder so small, then it will not crack. It can allow with the lithium in a way where the mechanical stress that is created is released because more and more, when you shrink the size, more and more silicon atoms are close to the surface. And comparatively, the ratio of silicon atoms in the core of the particle is a smaller and smaller ratio. So that has been known. And then you say, well, that's easy then. Let's just grind the damn thing and have a very fine powder, and that's it.
That's right.
Well, then people discover another problem. And the other problem is that the surface area of a powder that is nanoscale powder of silicon is way higher. So if you take a micron-sized powder of silicon and you grind it to make a powder that is, let's say, 100 nanometer particles, the surface area will multiply by 10 to something like 40, 50, 60 square meter per gram. And then you run into another problem. And that other problem is that when you put that in a battery, and during the first few days of what's called formation, you very slowly charge the battery and discharge the battery to create this fine pellicle that sits on top of the active material called SEI, solid electrolyte interface. Well, what happened is that there is just too much surface area, so you consume a lot of electrolyte that decompose against the very electrochemically active silicon area. So then people say, well, that's easy to solve. Now I'm going to basically either carbon coat the silicon or put the silicon inside the pores of something that are going to seal off so that there is no electrolyte contact with the silicon. And that's what people have been doing. And we did that about 15 years ago. And then you run into other problems that have to do with the ionic conductivity to get into the silicon and so on and so forth. Nanowires are fundamentally different, and they're fundamentally different for three basic reasons. The first reason is that the way you grow nanowire is by using a catalyst. And by using a catalyst, you can control the diameter of the nanowire. And the catalyst we use is extremely small. It's about 26 nanometers in diameter. So 26 nanometers is about 10 times the diameter of your DNA. That's very small. And when you make something that is that small in diameter, but very long, for example, 1 or 2 micron, it's like a very, very thin eyelash or a very thin hair, and therefore it's called one-dimensional, and that's the name of the company, OneD. A couple of things happen, and this is basically quantum physics. The first part is that you don't have to worry about how quickly you're going to decompose the silane gas that is used to make the nanowires, because a catalyst will make that reaction happen very fast with almost no waste and at very low cost. But at the same time, you will end up with all of the little hair of silicon having two properties. One is they all have more or less the same diameter, so you don't have to worry about the size of the silicon. And number two, the roots of the silicon are embedded into the graphene of the graphite. And that makes a perfect electrical contact. So now you have solved the first problem, which is how to control the shape and the size of the silicon. Now, the second aspect that is totally unique, and I'm going to describe it to you, is that the surface area of nanowires for the same amount of silicon is 2 orders of magnitude smaller than the surface area of a collection of nanoparticles of silicon. And that means that the electrolyte problem goes away. And I'm going to explain that in a very simple way. If you have a long, thin spaghetti, the surface area is that of the end point of the spaghetti on each side. And then the cylindrical shape of the spaghetti is basically the circumference times the length. Now that has a certain volume and a certain surface area. And imagine that it's made of silicon, not, pasta, basically. And now you break that spaghetti in two and you add the surface at the middle on each side of the break point, but you have not changed the volume. And then you break it in 4, and then in 8, and then in 16 and 32, until you end up with a collection of little particles that have all the same diameter as the diameter of the nanowires, or in this case, the spaghetti you started with. And what you have is that you have a much larger surface area. So that's the second reason why it's unique.
I see.
And then the third reason that is unique is, think about a light bulb that you're trying to light on your nightstand next to your bed. What are you going to do to light that light bulb? You're going to use an extension cord that on one end is connected to the light bulb, and on the other end is connected into the outlet in the wall. And what you're trying to do is the most efficient way to get the electrons to go from the wall to the light bulb. Think now about charging a battery. What you're doing when you plug the plug at the charging station into your car is that you're injecting electrons. And billions and trillions of electrons find their way into the anode. And they basically, each of them has to match with a lithium ion, and they have to marry each other inside the silicon. So you need to feed the silicon with electrons. And what better ways to do that to provide the electrons an extension cord made of silicon that is plugged into the graphite. And so the mobility after you have first charged the battery, the silicon becomes doped with lithium ion. And doping is a term in electronics to say that it changes the mobility of electrons. So the electrons that you're injecting into your battery can move extremely quickly in the silicon along the length of the nanowires. And the lithium ion can penetrate from the side along the radius. And they have a very, very short distance to travel. And then the electron and lithium ion marry each other, which means that with nanowires, you can charge 4.5 times faster than with graphite.
And that speed relates to C rate. It's power, right?
That's correct.
Yeah, good. So we like power. Good. Very detailed explanation. Thank you for that. And you covered a couple of my next topics with that detailed explanation, so I won't have to go through that now. Thank you. So, the expansion has been a long-term problem, and you've kind of explained how that's been solved, so that's really good news. We covered how it also translates into higher C rates, but what about the dry electrode coating? How does that play into this? Is this one of the innovations you described that we need to develop further to keep our competitive advantage on the right side?
Yeah, actually, this is a very good example of an invention that can dramatically increase performance of EV cells and decrease manufacturing cost. And so that's a perfect example. And it's something that, our CTO started working more than 10 years ago. As a matter of fact, one of the patents we have is co-inventor with a person that now works at Tesla, because that person was on our patent, then worked for Maxwell, and then Tesla acquired Maxwell. But fundamentally, why is dry electrode coating both good and hard? It's good because you eliminate the mixing of the various ingredient that goes into the anode into a solvent, which you have to evaporate. And mixing in the solvent and then evaporation later is actually costing a lot of energy. And therefore, if you can avoid that, it's good. Why is it hard? Well, one of the properties of mixing is that you're trying to get to something that is homogeneous. Just think about making crepes at home where you have to mix, the flour and the milk and so on, and you're trying to not have any bubbles and not have any clumps so that you have a perfectly wonderfully tasting crepe. Well, mixing the slurry in large EV cell factory is a really, really hard problem, even when you do it with a solvent like water-based solvent for the anode, because in a 30 gigawatt hour EV cell factory, if you are the production manager, you will receive every day a train load of graphite that is equal in weight to twice the weight of a 747. And in the following 24 hours, you have to mix this graphite with the binders and the solvent and make it a fluid that is extremely uniform, and then coat it on the copper foil at about 1 meter per second and 100 micron thick, plus or minus 1%, perfectly uniform with no imperfection. That's difficult. Now imagine you get rid of the solvent. Now you have to mix stuff in solid state. You have different powders, and you don't have the benefit of the viscosity of the fluid or the solvent. And achieving uniformity is very hard. So if you have one type of let's say, powder, let's say it's graphite, and a few percentage points of binder powders, then you can easily do that. And that's what Tesla is doing today in producing graphite only dry coated anode for the 4680 cells. But now imagine somebody comes along and say, why don't you put a powder of a silicon additive and you dry mixing that? And then you're going to do dry coating those electrodes. Well, here is the problem. We just talked about the fact that the silicon can absorb a lot more lithium. So when you make a dry coated anode electrode and you have mixed the graphite and the silicon additive powder, it's very easy to have slight uniformities. So this square inch of the electrode has a little bit more silicon, and that square inch has a little bit less silicon. And remember, in the batteries, in the battery pack of an EV, you have 800 square meters of separator. That means you have the anode and the cathode facing each other over a very large area. And you know that in order to avoid problems, safety problems, you need to match the capacity of the cathode and the capacity of the anode. Now, if you cannot do that precisely enough, you will have run safety problems. Okay? And so achieving this uniformity of the silicon inside the graphite anode layers is very hard. Now, we solved that problem in a very elegant way, and we're the only one in the world doing that. We patented that by fusing the silicon nanowires to the graphite. So each graphite particles may have 50,000, 100,000 nanowires on it. They mechanically attach. And so you don't have any mixing of an additive of silicon with the graphite. It's already pre-mixed, if you wish, and pre-mixed where it's uniform at the few particle level.
So
and so
you solve I'm sorry to interrupt. You solve the silicon distribution problem, but there's still the other bits, right? You've got maybe some synthetic graphite or coatings, and those are still there, right?
Yeah, so there is another problem that exists, is that in order to make this self-standing film, you have to use different binders than you use in a normal wet coating. One example of such binder is PTFE, which is Teflon. And PTFE, when you compress it between rollers, create little fibrils that act like the fabric that makes the self-standing film self-standing, basically. And then you can press that onto the copper foil. Well, Teflon is not easy to stick to. And so whatever other things you're doing, you have to find a way that during the dry electrode coating, when you take the mixed powder that is dry mixed and you push it in between rollers to make this very thin pancake, you need a way to create an adhesion between the particles that is very, very good. And our CTO, Yimin Zhu, invented a different type that doesn't exist in anywhere else of surface treatment. So the Synanode product we produce has a very, very thin layer that is very unique, about 2 nanometers thick, that covers both the silicon and the graphite and really helps in developing those self-standing film. So that tells you that there is a lot of work that has gone on over the last 10 years to not only address the silicon issues, but the manufacturing issues as well.
All right. So we've covered a lot of what is OneD's technology here, and you've answered a lot of really good questions. So thank you. We talked a little bit about some of the cathode chemistries, but without going through the alphabet soup of all the different things that's happening out there on the cathode side, what should we be looking for? Which ones are going to be the winners? Do you have any foresight, any predictors for our subscribership here?
Well, I think that, LFP has grown dramatically over the last few years, essentially for cost reason. The fundamental patents protecting LFP expired, and Chinese suppliers, which previously were limited to the Chinese market, now can export worldwide. And because everybody is looking for cost reduction, LFP increase in market share, and that's going to probably continue. But LFP has other drawback in terms of energy density and so on. So we think that, the nickel-rich NCAs, NMCA, and NMC 811 and NMC 622 are continuing to be very valuable. And depending on what part of the EV segmentation, you know, OEMs will have different chemistries for different price segment. I think that it's unlikely in between now and the end of the decade that you will see a complete change in the chemistries. I think it's going to be more of an evolution, and it's going to be an evolution for economy of scale reasons, cost reasons, and risks reasons. And at the end of the day, the large producers, for example, Umicore's and BASF, will continue to produce NMC and NCA cathode material that is going to be used in more than 50% of all the EV cells. And it's unlikely that that's going to change. There will be, of course, variation on a theme. One that we think is a very elegant cathode is NMC doped with aluminum, so NMCA. It has a higher energy density and it can be quite safe. So it has a lot of the right properties. And as production continues to increase, the cost will continue to go down.
Very nice. So, we talked about Tesla a couple of times here. You may know some history, having been a viewer of our teardowns. We had the wonderful experience of tearing down a structural battery pack for a Model Y with the 4680 cells in it. And one of our missions was to try to determine how many of the battery day claims had been achieved with this 4680. And we were a little bit disappointed in the energy density. And when we looked at the construction of the anode, we didn't find much silicon, if any, in it. And that kind of explained why they didn't reach their energy density targets on that first iteration. Do you know why? And do you also know whether or not they finally achieved it with this latest generation that's said to have a lot more energy density? So,
yeah,
what can you tell us?
Well, without talking about anything that I learned under NDA from any of our customers, I think that people should realize that what OEM cares the most about, first and foremost, is safety and cost. Performance is very important, but is number 3. And what happened when you increase the size of the battery, going, for example, from 18650 to 21700 to 4680, you increase the amount of energy in the can. And the amount of energy means that you need to manage the heat. And when you actually charge at a high C rate, that's an enormous amount of heat. And so I think that doing that safely is something that requires very, very careful experimentation. It takes time. The second is cost. And definitely dry electrode coating on the anode side has reduced the cost of Tesla 4690 or 4680. And they've explained that very well. So that cost reduction is extremely attractive from 2 points of view. The per cell cost goes down, but also the throughput of the factory in number of cell per, let's say, square acre goes up, so that you can actually serve more EVs with the same size factory once you switch over to dry electrode coating. So I would imagine, just like anybody else, that the increase in performance, i.e. to add the silicon to it, goes next. And if you think about the company that has the most experience in cylindrical cell in the world, that's Panasonic. Panasonic has produced more than 10 billion cylindrical cells. And they announced early this year that they were delaying by 1 year until 2024 their own 4680 cells. And they've all the expertise that exists in the world, and they've been doing it for a long period of time. And what that shows is that in large-scale manufacturing, if you're trying to manage these 3 things, safety, cost, and performance, you need a step-by-step approach rather than rushing to do something that is unsafe or that is going to decrease your yields or that is not ready for prime time. And I think it's just a matter of evolution, recognizing you don't make a baby in 1 month or even 5 months, you make it in 9 months. And the same thing happens in large-scale production of 4680.
All right, that's a pretty fair answer. So we're running out of time here, but I do have this burgeoning question when I think about all of your skills and your experiences going way back, and now your, intimate knowledge of the battery industry and apparently Tesla's various industries. The one that comes together that mystifies me when you think about the far-reaching implications is Elon Musk's Neuralink technology. You have quite a bit of knowledge about the brain and how it works, and how that might, augment the human, if you will. Certainly, starting with people that are handicapped, perhaps even with hearing problems, all the way to the non-handicapped person looking to have telepathic communication with another human. So what are your thoughts? This is an interesting technology, and you're one of the few people that I can consult that would have a wide range of knowledge on the subject. So,
Well, in full disclosure, my son did an MT PhD, and then in actually neuroscience. The MD was at Stanford, and the PhD was in the immunology of the brain, and he now does neurology at UCSF. And so I talked to him about that. I will not tell you exactly what he told me, but he knows about 1,000,000 times more than I do about the brain, and certainly is aware of what Neuralinks does. I would venture to say that things that do with the human brain and things that do with healthcare are drastically different than batteries or putting, satellite in orbit. And so I would say you cannot take the same kind of risks. And things that we don't know is many, many times, many orders of magnitude greater. If you think about SpaceX achievement, it's phenomenal. On the technical side, the reuse of the boosters is incredible. On the economic side, achieving 80% market share is fantastic of all the global satellites. But it's all about physics, and physics is pretty well understood. And even at batteries, you have, of course, chemistry and you have manufacturing, but it's a lot more known than the human brain or, the healthcare of patients. So I would leave it at that. I would say I personally would be extraordinarily cautious in extrapolating a skill set that has worked in two industries to a fantastic level and trying to tackle something on the side that is as both complex and dangerous as dealing with the brain. So I will leave it at that.
All right. Very carefully worded answer. I appreciate that. And I might recommend that if you ever do reinvent yourself, you might consider politics.
I have no skill whatsoever.
Okay. Well, anyway, I do appreciate that clarity. And with that, we've kind of run us out of time here. I want to thank you for participating today and enlightening all of our viewers out there in the internet land, and I'm sure they appreciate it as well. So, very nice to meet you. And,
thank you very much.
Have a good day, sir.